Okay, everyone, welcome back for a Friday. We're ready for the weekend, right, Noah? Very definitely. No, I might suggest that rather than type directly into your computer that you can do that, but you're going to be better off if you learn to write it down with your pen and pencil, and then from that put it into your computer. That's part of the learning process, okay?
Well, my hammer gets right down.
Oh, okay. Also, I don't permit it here, and no one's been doing it, but that's fine. The practice that some people have of photographing the blackboard, of sitting back and then just taking their camera and once in a while taking a picture of the board and they think they're taking notes. That doesn't work either. The process of forming letters and words on a piece of paper or making a drawing is far preferable. Okay? You want to do it the easy way, fine, but you pay the price for doing it the easy way, which is poor performance. Okay? All right, but you guys are here. What can I say? All right? We're into electricity, and eventually we're going to be getting into magnetism. But so far, we have learned about electrical charges and that opposite charges attract, and that like charges repel each other. And what we have, we can draw that by saying that like charges push each other apart, and if they are unlike charges, then they are attracted to each other. And they must exert equal and opposite forces on each other as well. That's because of Newton's third law. Now, what we have also discovered, and we haven't got time to go into it, is that all matter is made up of equal numbers of positive and negative charge. And I mentioned this, that you can transfer electrical charge from one object to another. And what I can say here is actually I can say all neutral matter. And the natural state of matter is to be in a state of neutrality. This is because if there is any separation of the charge, because opposites attract, if the charge can move, it will, and it will try and redistribute itself so that balance is restored. So that when I shuffle my feet, or when you shuffle yourself in your car seat in the wintertime, we find that a static charge builds up. Then when you get out of the car, a spark will occur. This is because the charges attract each other, and the charges literally leap through the air. They leap through the air. That's what causes that spark and that little shock that you get. And of course, I mentioned on a huge scale, we wind up with lightning. Lightning can occur in lightning. Now, we should mention something else. We also showed that depending on the situation, the separation of charge either stays or it eventually goes away. And by experimenting, we find that there are materials that will allow electrical charge to flow through them. Most metals fit into that category. And liquids that are impure, like our body liquids, you're mostly your salt. Your body is something that will allow charge to flow through it. And we have two kinds of substances, conductors, permit charge to flow. Examples are most metals, many liquids are conductors, particularly salt, water, and so forth. But then there are insulators. and insulators do not permit charge to flow. And an example is dry air. If air is moist, if the air is too moist and too humid, a little bit of charge can flow through it, okay? Moist air is pretty much an insulator too, but less so. So that if you try to charge something up electrostatically, it doesn't work very well on a rainy day. The humidity in the air lets the charge drain off, okay? But dry air, most plastics, not all though, most plastics are insulators. Glass, ceramics, these sorts of things. These are such that the electrical charge will not flow through them. Okay? So we have conductors and insulators. Water, surprisingly, purified, highly purified water, which you do not encounter in your everyday life. You encounter highly purified water upstairs in the chemistry department. That's about the only place you're going to find it, okay? The slightest impurity in water turns it into a conductor, okay? Almost all water that you're going to encounter is going to be impure. It takes the tiniest bit of anything dissolved in it and suddenly it conducts electricity, okay? Purified water is an insulator, but we all know that you don't stand outside during a thunderstorm in the middle of the lake in a metal boat. This is a bad idea. This is a bad idea, okay? Now, all matter, all neutral matter is made of equal numbers of plus or minus charge, but you can upset the balance. Nature and you can upset that balance. And when that happens, we say that the object is electrically charged. You see, right now, if I'm full of positive and negative charges, and you're full of positive and negative charges, aren't all of the positive charges in me pushed away from the positive charges in you? Yes. And the negative charges in me are pushed away from the negative charges in you? Yes. So how come we don't fly apart? Because the negative charges in me are also attracted to the positive charges in you, and the positive charges in me are attracted to the negative particles. So it balances out. So as long as there are equal numbers of charge in an object, it is effectively not charged at all. But by rubbing things, most notably, you can upset the balance. That's why rubbing something will upset the balance. And that rubbing can occur in nature. Now, because impure water is a conductor, if we have a cloud, a thundercloud, if the storm gets violent enough and the updraft gets strong enough and certain conditions are met, you will have ice crystals up in the cloud. If it gets violent and the ice crystals get big enough, what do you get? You get hail. You get hail. But you can have ice crystals up there and not have them falling to the ground. The wind can support them. Ice is an insulator. Okay, when you freeze water, you don't allow the electrical charges to come through, so ice is pretty much an insulator, period, whether it's pure water or not. So if ice builds up and you've got the wind going, you have the ice getting rubbed against itself. That means conditions are right to transfer charge. And you can get a huge buildup here across the cloud, and when that buildup gets big enough, the negatives hate each other. It's usually the negatives that move. They love the positive charges, and so they leap in a flash of lightning over to the other part of the cloud. Most of the lightning in a thunderstorm is within the cloud, and of course you can't see through the cloud, so you can't see the light that comes from the lightning inside the cloud. But you do hear the thunder. The lightning heats the air to thousands of degrees. It creates a vacuum there. When it collapses back in, you have this tremendous sound, and we call that thunder. Of course, it is also possible, if the buildup is large enough, because raindrops are falling, the raindrops can carry the charge from the cloud to the ground. And so you can get a huge buildup of electrical charge between the ground and the cloud, even though the ground and the cloud might be 3,000 or 4,000 feet apart. And eventually it builds up to where it can't stand it anymore, and then you have cloud to ground lightning. God help you if you happen to be there. If you happen to be standing there, because you are essentially a conductor, you decrease the distance a little bit, and it's more likely that the lightning is going to hit you. And when the lightning hits you, unfortunately, the human body is controlled by electrical impulses. Your nerves actually respond to electrical impulses, and your muscles do as well. And this is why electricity traveling through the body can kill you. If it arrests the heart, that obviously is bad. But also because it's hot, it can boil your blood and cause your veins to explode. Well, obviously that's a major injury, and you have to watch for that. The first thing you can do if someone has been struck by lightning is administer CPR. Make sure they're breathing. I don't care what's happened. If they're not breathing, they're not going to survive it. If their heart's not beating, the heart is a muscle. And so if you are going to get hit by lightning, this has happened. If you suddenly feel all the hairs on your body start to stand on end, it means you're getting electrically charged. You're about to get struck by lightning. And the best thing you can do is to get down on all fours. And some people say, they'll say in the movie Twister, that's because your butt's in the air and that's the most rugged orifice in your body. No, that's just movie making. You do this because if you remember that electrical charge hates itself, right? If the electrical charge enters your body, it's going to spread out. And if you have your arms like this, it's going to stay away from the center of your body where your heart is. You could still bleed, burn, all kinds of bad things could happen, but you won't stop the heart. But if you have one hand like this, the lightning can go across your body. Well, now you could be in trouble. All right? It's a bad idea to go climbing on the tops of hills in the middle of a thunderstorm. Okay? Bad idea. What is one of the safest places in a thunderstorm? Most people know this. What's one of the safest places you could be? A car. Trouble is, that's not true anymore. You see, you're safe in. Why would you be safe in a car? Someone take a stab at it. Why are you safe in a car? People say the rubber tires. Excuse me. The lightning just jumped 2,000 feet from the cloud. Do you think the 2 feet to the ground or the 1 foot from the ground to the tires is that important? No. It's because when the charge enters the metal shell of the car, it spreads out because it hates itself. And it goes around you instead of through you. It goes around you. Of course, if the car is plastic or fiberglass, which is an insulator, that doesn't work anymore. All right? Another bad place is if you are by a tree. Okay? A tree is filled with liquid. It's drawing water up. The tree is a conductor. If the electricity strikes the tree from the lightning First of all, it's so hot, it'll boil the water inside the tree, and the tree will explode. That's why branches are blown off of trees when they're struck by lightning. The boiling water blows that part of the tree off. But here's a nice juicy person next to the tree. If you decide that you're going to get under the tree for shelter, here's a nice juicy person who's got a lot more water in them than the tree does, and the electrical charge just might decide to come in and jump over to you and then go down. All right? Taking a shower in the middle of a thunderstorm, not a good idea if you have metal plumbing, and so on and so forth. Now, this is important. Lightning is interesting because lightning represents moving electric charge. It's moving. It's trying to get back, but it's instantaneous. It's a huge movement of charge, boom, and then it's all over. So moving electric charge is given a name. Moving electric charge is called an electric current. In most cases, it is the negative charge we have found that does the moving around, but in certain cases, particularly when liquids are involved, the positive charges can be moving as well. But in most cases, like in wires and so forth, the electric current is tiny negatively charged particles that are moving. And we call moving electric charge is called an electric current. Now, we get into a major question. We know that there is this electric force between two charged objects. So we know that opposite charges attract and like charges repel. Even if they're several feet apart. They do not have to be, I'm going to show you, they do not have to be real close to each other. They can be several feet apart. This wand that I'm putting together is an electric wand. It's known as a Van de Graaff generator. Now hopefully it's going to work. We'll just have to see. Inside, let's see. Oh, it's not going to work. All right. It's not. Try it one more time. Now, sometimes it works and sometimes it sticks. And there we go. Ha! Thank you. Okay. Now, what I've got here is a very thin piece of foil. Okay. And if I charge this up, you'll notice that it is repelled by the wand. And no matter where I put the wand, come on, let's get it back for the camera. No matter where I put it, it is repelled. Also notice that all the loops on it are open because charge has been transferred. The moment it touches my hand, it collapses. The moment it touches my hand, it collapses because the charge leaves the metal, goes into me, and flows all over the place. I could press this, charge it up again, touch it. Once I had it stick up on the ceiling, it stayed there for several days, okay? Notice it's always pushed away from the rod. Always pushed away. That's because it has the same charge as the rod. And the individual parts of it are pushed away from each other until the charge is gone. Until the charge is gone, then it all collapses. The question is, how does this know that this is there when there's several feet between it? How can it possibly know? And if I were to do this in space, the air is not needed for this to happen. It does not depend on the air. How does the foil know that the rod is below it? Okay? Turning the rod on inside here is a piece of rubber. That's what's inside there. And it goes around and it rubs. And it generates an electric charge. The question is, how do the charges know that the other charges are there? Well, that is quantum electrodynamics, and that is advanced graduate school physics. And we can't get into that. But here is what we argue. Listen carefully. This is a fundamental change in thinking. There's the blackboard, yeah. Whiteboard, okay? This is space totally devoid of anything. The entire place is empty. There's nothing in it. If I take a charge, let's say it's a positive charge, and I put it here, what I'm going to argue is that this charge changes the space around it. And once I put this electric charge here, all of this space is now different from what it was before. Now, how do I know that? Because I can take an object like this, not quite so complicated, and charge it up, and this is now what I call a test charge. See, right, if I remove this, notice that it falls. The space when it falls is different than the space when it goes up. This somehow changes the space around us, and this can sense it. We call that change in the space an electric field. We argue that this charge produces an electric field. Now, how do I know this? Because if I put what I call a test charge, a test charge is this that has been positively charged. And if I put that in this space, it's not going to experience any electrical force whatsoever. In this space right now, this experiences no electric force because there's no other charge to attract it or repel it. But the moment I put the wand here, suddenly it experiences an electric force away from that positive charge. We call this the source charge. The source charge produces an electric field around it in every direction. We say that an electric charge modifies the space around it, producing an electric field. This is real, people. This is real because I can measure it. If I take my positive charge here and it doesn't experience any electric force, then there's no electric field. But if it does experience an electric force, then the direction that it experiences that force, that is the direction of the electric field. So the source charge produces an electric field around it. Are there any questions at this point? Now, we are visual creatures. So what we would like to do is to somehow visualize this electric field. What does it look like? Well, we can use the test charge to produce a map of the electric field around it. What you see is, and I think you'll see that once I get this thing charged, that no matter where I position the rod or how I position it, this thing is always pushed straight away from the rod. Let's look at that. Once it wound up there for a week. Couldn't get up there. Eventually a humid day came by and it fell down. Okay? We won't go into how it's attracted to the board, but essentially there are charges in the board, some weird stuff goes on. Clearly, wherever I put this test charge, if I put the test charge down, and then draw, here's our source charge. If I put the test charge here, no matter where I put it above this charge, the electric force is going to be away from that source charge. And if I put it below, which way is it going to be? It's going to be pushed down, correct? What if I put it here, to the right? See, what I'm going to wind up drawing is a set of field lines. And we can call this the electric field. That's the vector sign, which means it has a direction. And by the way, we should specify this. I always like to specifically say things. We notice that once I get this charged up, come on, that it comes down until it gets closer. So evidently the electric force gets larger the closer the objects get to each other. So that as you move charges apart, the electric force gets weaker. It depends on how far apart they are. The closer the charges are together, the stronger is the force. The further apart they are, the weaker is the force. It actually obeys what's called an inverse square law. We don't have to go into that much detail. But you must know that the force is stronger the closer the charges are together. Okay? Now, if we continue to do this, we would technically draw an infinite number of lines. Have you ever seen a sea urchin or a porcupine that curls up to try and protect itself? Imagine those barbs sticking out are the electric field lines. That's kind of like what you're going to get for a positive charge. We also know that you can have strong charges, like you get in lightning, or weak charges, like you get here. Actually, this produces a pretty big field, okay? But it's not like lightning. Lightning is a million times bigger, okay? So we would like to have a way of drawing the strength of the field. Well, we can do that. We can agree that for weak charges, we only draw a few lines. So if I have a positive source charge, I take that test charge, move it around, see which way it's pushed. The way it is, notice this, the direction of the field is the direction of the electric force on a positive test charge. What would happen if I replaced the positive charge with a negative charge? Would it be attracted or repelled from that? Be attracted. So we'll talk about that. But for a positive charge, we can draw it like this, with the understanding that obviously I haven't drawn everything in. Also, there are lines pointing out like this in all directions. But if I only draw 4, that means it's a weak charge. If it's twice as strong, then the convention is that I draw twice as many lines. So if I had a charge that was twice as strong, then I draw twice as many lines. This is a medium charge, a medium positive charge. If I have another one which is twice as strong again, then I need to draw in twice as many lines again. So I draw another one in. I'm a terrible artist. These should all be equally spaced, pointing out, but I haven't got time to do. This is a strong charge. And we said that the electric force gets larger as they're closer together. So if this were my test charge, and I had it here, as it gets closer, the electric force gets larger. Well, what's really going on is, notice that the lines get closer together as you get near the center. These lines, they're this far apart here, they're much closer and closer. These lines get closer together the closer you get to the charge. It turns out that this is how you represent the strength of the electric field. The density of the field lines, density is the closeness of the field lines. The density or the closeness of the field lines is proportional to, or represents, you could say, the strength of the field. When the lines are close together, whoops, I can't spell strength, strength of the field. The density of the field lines, how close they are. So looking at these, you see that as you get near the positive charge, the lines get closer together. And as you move away, the lines get further apart. That's true for all of these. This is true for all of them. Now, what would happen if I used my same positive test charge? What would happen if this were a negative charge? Notice they come out of positive charges. But if this is a negative charge, and I put my positive test charge here, is it going to be attracted or repelled? Attracted. And I'm supposed to draw lines in the direction of the force on it. That means that I'm going to have to reverse all of these lines. The field lines come out of positive charges but they go in to negative charges. If I drew this one, if I change this to a negative charge, wherever I put a positive test charge, it's going to be drawn in. So the field lines enter negative charges. On the other hand, the field lines exit positive charges. The field lines exit positive charges, but they enter negative charges. The density of the field lines is proportional to the strength of the field. So that we draw more lines, or when the lines, if the lines are coming together, what's happening? Let's look at this. Let's take another look at that for a little while. Suppose the field lines are doing this. What is happening to the field strength as I move down on the board? Are they getting closer or further apart? Don't make this hard. Are they getting closer or further apart? Closer. The field is getting stronger as I go this way. What if they're doing that? See, watch. If I just take away the source, and, well, what if the field lines are doing this? They're getting further apart. They're getting weaker as you go this way up. They're getting stronger as you go down. So the density of the field lines is proportional to the strength of the field. They enter negative charges. They exit positive charges. What I'm doing is I'm writing a set of rules. All right. If I put a positive test charge here, this is the electric field from something, I don't care what it's from. I put a positive charge there. The field is pointing down and somewhat to the right. Well, that means if I put that test charge there, that the electric force is going to be in the same direction. That if I release the charge at that point, it's going to accelerate in the direction of the field line, if it's a positive charge. So, for a positive test charge, the direction of the electric force or you can write it either way, electric field is the direction of the electric force on that charge. You can read this backwards. For a positive test charge, the direction of the electric force on the test charge is the direction of the electric field. Go either way. So if the electric field is this way, like that, and I put a positive charge there, the force on it is that same way. It's that same way. What would happen if I put a negative charge there? What would happen? Obviously, it would go the other way. You could use a negative test charge. So if the electric field is up, the force on a positive charge put there is going to be up. The force on a negative charge put there is going to be down. And so on and so forth. For a positive test charge, the direction of the electric field is the direction of the electric force on a test charge. Okay? Okay? Reverse it. For a test charge, the direction of the electric field is the opposite of the direction of the electric force. Okay? Positive charges have a force with the field. If I put a negative charge here, the electric force would be that way. Okay? It would be that way. If you think about it, this is coming out of a positive charge someplace, and so it's going to be attracted to that. Okay? Questions or comments? Questions or comments? Now, there's nothing that says you can't combine charges to produce complicated electric fields. One thing we find, these are the rules for field lines. These are the field line rules. I think they're all here now. Okay, here's one. Here's two. Here's three. And there's a number 4. What happens if you have 2 electric charges producing a field? 2 source charges. Well, if you put a test charge in there, it's going to feel some kind of electric force, right? But there's going to be one, and only one, direction of that electric force. I don't care how many charges I peg down to be source charges. If I take a test charge and put it someplace, if there's an electric field there, there is one and only one direction that it's going to experience a force. It can't try to decide on 2 directions. The result, field lines never cross. There is one and only one resulting direction for the electric field. They never cross. They come out of negative, or they go into negative charges, exit positive charges. They never cross. The density is proportional to the strength of the field. And the direction of the electric field is the direction of the electric force on a positive test charge that you put there. These are all illuminated in the textbook in Chapter 6. Read Chapter 6. Questions or comments? Let's kind of put all this together. A very common configuration that occurs in nature quite a bit is 2 equal but opposite charges. This often happens with molecules. Molecules can be electrically charged or polar, and a very common configuration is a positive charge and a negative charge of equal amount. These are both source charges. These are both source charges. Now I take my test charge and I move it around to map out the field. Well, if I put it in between, it's going to be always pushed away from the positive and attracted to the negative. So we'll get something like that. And then if you continue to do it, you'll wind up drawing something that starts to look, it's in the textbook, I'm a terrible artist. With these coming out of the positive and going into the negative. I could draw another one here. That. Now these never stop. They come back and shoot. It goes up way out here and comes back. They come out of the positive charge, and then they curl around back, going into the negative charge. Where are they most tightly packed together? Don't make this hard. In the middle. This is where the field is strongest between them. Then as they spread out, it gets much weaker. Much weaker. Okay? Much weaker. Notice up here that this field line is pointing to the left. That means if I were to put a positive charge there, there would be an electric force on that to the left. If I put it over here, there would be a force on it down and to the right. It's being pushed from this but pulled to this, and when they combine, there's only one direction, and that is the direction of the field line. What would happen if I put a negative charge here? Well now it would be pushed that way. Okay? This is called a dipole. This is called an electric dipole. And finally, we've got 2 minutes. One very popular configuration is to take 2 plates, these are shown in the textbook, 2 metal plates, and charge them up with equal and opposite charges. And if you look in the textbook, what you will see is that the field lines point straight away from the positives to the negatives, and they are perfectly parallel to each other. They are equally spaced. This means that in between the 2 plates, if they're close together, because the field lines are not coming together or going apart, the electric field is absolutely uniform between the 2 plates, no matter where you are in the region between the 2 of them. This is used quite often. Just 2 plates, equally charged, you get the metal plates of course, you get a perfectly uniform field. That's not uniform, okay? No way. So let's stop right there, and we'll pick this up on Monday. Have a great weekend. Be safe. Keep your mask on. People are getting sloppy. Cases are going up. You cannot let down your guard. All right, take care.